So, my name is Pavel Pokorný, and today we are going to talk about numbers. In mathematics, we often work with numbers. So what kind of numbers, what sets we have? We have the set of natural numbers, positive integers. This is the set having the numbers 1, 2, 3, and so on. In this set, we have some operations. We can add two numbers. 2 plus 3 is 5. And then we can ask what was the second number to give the result 5. The answer is 5 minus 2, which is 3. So we can subtract positive integers. But sometimes, if we subtract 2 minus 5, no result, no positive integer. So we can generalize this set into the set of all integers. The set of all integers is denoted by capital Z, and this is the set having these numbers 1, 2, 3, and so on, and having the number 0, and having the minus, the negative numbers. Then we can multiply numbers. Say 2 times 3 is 6. And then again, we can ask what was the second argument, what was the second number to give the result 6 when multiplied by 2. And the result is 6 divided by 2. But sometimes, if we use this operation, division, we have no result. Say 6 divided by 5 is not an integer. So we introduce rational numbers denoted by capital Q. And this is the set of all the numbers in the form of a fraction, some p divided by small q, such that p and q are integers and q is different from 0. If we visualize these sets, then we can use the real line or just line, and positive integers are numbers corresponding to these points. If we add 0 and negative integers, we get a system of points like that. And if we visualize all the rational numbers, we get very many points in this line. It looks like almost they fill the line, but they don't. To fill the line completely, we need real numbers, or reals. And this is the set of all the numbers that can be written as possible sign, which may be plus or minus, some integer part, say 12, a decimal point. In English, it's really a point. In Czech literature, it's a comma, and possibly a finite or infinite sequence of digits. So this is an example of a real number. If the sign is plus, we usually omit the sign. And these numbers are good because they fill the line completely. Then we have some operations in real numbers, especially square, which is multiplication by itself. If we have some number, say 5 squared is 25, and then we can ask what was the base to give the result 25, and the result is square root of 25. But if we change the sign and want the square to be negative, then no real result exists. And for this purpose, we generalize real numbers to complex numbers, and this is the set of all the expressions in the form a plus ib, where a and b are reals, and I is the special object satisfying that I squared is minus 1. This is a new symbol, new object, which is very useful. You can think of a complex number as a box for two real numbers. And this is a very useful concept, very useful set of numbers, often used in physics. If you consider the pendulum, then the energy is pumped into the positional form of energy and kinetic form of energy. So we have two forms of energy, or two variables, and this is very convenient to bind these two variables into a single number. But in the first semester, we will most often work with real numbers. Then, instead of having just one number, we often work with sets of numbers. So an important term is interval. An open interval, say from 2 to 3, is the set of all real numbers such that 2 is less than x is less than 3. And this can be visualized using this segment. And the endpoints do not belong to the interval, so we visualize this using empty bullets. This is an open interval. A closed interval is denoted in English literature by square bracket, and this is the set of all real x such that 2 is less than or equal to x, less than or equal to 3. And this can be visualized as a segment with the full bullets denoting the endpoints do belong to the set. In the Czech literature, instead of square brackets, they use angle brackets in the Czech literature. There are just a few differences in the mathematical notation between the English and the Czech literature. But the open interval is the same, using the round brackets. And then we can combine these two. We can have an interval which is left closed and right open, or vice versa. That means 2 belongs to the set and 3 does not. And here the left hand side point does not belong, and the 3 belongs to the set. Then when we have sets of numbers, we can consider operations between these sets. We can have intersection. And generally for any set, if we have set A and set B, then intersection is the set of all the elements that belong to both of the two sets. And we have union of two sets, which is the set of all the points that belong to A or to B. Intersection is denoted by A intersection B, and union is denoted by A union B. Yes, this is under U, and this is some counterpart, so it's upside down. These two operations between sets correspond to a similar operation between statements, between propositions, between sentences. We can have a sentence A and sentence B, which each of them may be either false or true. 0 means false. False. Say, if I say, I am a lady, it's a false statement. If say, I am happy, it's a true statement. So 0 stands for false and 1 stands for true. And similar to intersection, we can have conjunction, which is written and. And this conjunction is true only if both of them are true. And this is a similar symbol to intersection because it corresponds to this. If the statement A is the given element is in the set A, and if the statement B is the given element is in the set B, then the statement A and B corresponds to the intersection of the two sets. Yes? Once more? Yeah, thank you. Thank you very much. Yeah, thank you very much. Yeah. It looks better. Thank you. Thank you. I love it. I love it when you find some mistake. It's so nice that sometimes I have a temptation to make intentional mistakes, to give you the chance, to give you the opportunity to react. Fortunately, I make enough mistakes even without knowing. And so this was conjunction, and we have disjunction, A or B, which is true when at least one of the two statements is true. And then for sets, if we work in some space and we have some set, then we can consider the complement. The complement, český doplněk, the complement of a set is the set of all the elements that do not belong to the original set. In this case, we must say complement where? What is the working space? Yeah, so that was for the numbers and for the intervals and for the sets. And in the next chapter, we will talk about lower bound, upper bound, and infimum and supremum.